Alrighty, we're on to 6-4. First off, 6-4 does not have any new vocab. It's an application section. So we are going to discuss story problems, applications using these things. And I'm going to kind of cover three major types of problems you've seen. And you've seen me mention some of these already when we've talked about mixture type things. It's like coins. I know it seems a weird thing to call mixture, but they are mixture type problems. We've had problems like these. So, anyway, before we do that, though, I want to talk briefly about the different methods for solving linear equations, and we've talked about these. You've practiced all of them. First off, it's graphing, and it says when you want to visual display the equation or when you want to estimate a solution. Again, because the reason we say estimate is because you may not be the most accurate at graphing. Your pencil might be thicker one day, or hand shaky like mine. Whatever. But so graphing is not the most valid way to solve these, in my opinion. But again, it can be quick, can be easy if they're in the right format, and a whole lot less algebraically intensive. Substitution's a fun one. It says when one equation is already solved for one of the variables, or when it's easy to solve for one of the variables, use that. If there's a bunch of fractions and stuff involved, probably not as much fun. Then we have elimination. It says when the coefficients of one variable are the same or opposite, or when it's not convenient to use graphing or substitution. I like this when I have fractions involved too, because you can easily multiply one or both equations, as we've seen, with a factor that can wipe out the denominators, and at the same time, make equal or opposite coefficients, making it easier to use elimination. So that's the way I look at this one. It's probably my favorite method, I think, because my brain thinks that way. I look for, how do these match up, kind of thing. And again, substitution is the one I think is a little more algebraically intensive, and graphing is the one that is not as reliable. The first type of problem we're going to address today is mixtures. Break-even point, rather. I'm sorry. Systems of equations are useful for modeling problems involving mixtures, rates, and break-even points. I want to make sure you understand what that is. A break-even point for a business is the point at which income equals expenses. So in other words, they're no longer in debt from their work, but they're not making any profit yet. We call it the break-even point. The graph shows a break-even point for one business. If we take a look here, if income, so this is the money that they're bringing in, right? So obviously it starts at 0. When it crosses the expenses line, notice the expenses line does not start at 0. That's because that could be like your rent you pay at the beginning, right? And then when you buy products, your expenses goes up, whatever you're selling. But then when you are selling those things, you start making a little bit of money, and at the point where you make enough money that it covers, rent and other expenses and the cost of the materials that you've bought so far, that is your break-even point. Everything past that is profit. And we take a look here, and this is that whole profit area, right? It's the profit area. Any combination in over here, right, creates a profit is the idea. But we don't generally solve these using graphing, but it's kind of nice to see what it looks like. It says, notice for the values of y in the red line represent dollars, again expenses. The value of the y is income, so y is used to represent both expenses and income. And this is why this works out so well, because we get to find when the two overlap. Otherwise, it wouldn't be a system of equations. Okay, before we actually solve, again, I want to look at the little think on the side. These are important. They're in your book. I don't know if you've noticed them. I know I've drawn your attention to them before, but it says the break-even point is when income equals expenses. So again, you're going to write one equation for income, one equation for expenses. You find out where they intersect, and that creates your break-even point. So the first example here is a fashion designer makes and sells hats. The materials for each hat cost $5.50. So again, it's $5.50 to actually make the hat. So he isn't selling it, he's in the hole $5.50 right off the bat. The hats sell for $12.50 each. So you can see here he makes, $7 off of each hat. The designer spends $1,400 on advertising. So there's a cost before you even start making a hat, before you even buy materials for a hat. Boom, $1,400 out the door. How many hats must the designer sell to break even? So if it weren't for this $1,400, every hat would automatically be profit, assuming they're sold right away. So you're going to write a system of equations. X is the number of hats sold, so this is important. These are all going to follow this same pattern. X is the number of hats sold. Y is the number of dollars or expenses of income. So again, Y represents two things, expenses and income. It's kind of a strange concept, but we're writing two lines. So in the first one, the expense equation. So you're writing two types of equations. Your Y, right, your expense, is $5.50 for each hat. That comes from here. And the $1,400 you spent on advertising. That's your expenses. Even if you sell 0 hats, $1,400 in the hole. Sell 1 hat, well, then you've got $1,400 plus $5.50 that you owe before you even sell the hat. Now, you're going to write a second equation called the income equation. Usually these are simpler. $1,250 times the number of hats sold. Now, X represents hats no matter what. Here, technically, hats made. Here, technically, hats sold, but we're just going to say it's hats. So, expense equation, income equation. Two equations. So when I ask you, if you ask for help, I'm going to say, did you write an expense equation? Did you write an income equation? Your answer better be yes to that. Alrighty, so choose a method. Use substitution since both equations are solved for Y. This is kind of cool. So basically, you notice here, this Y and this Y at the break-even point only are the same thing. That's the whole point, is when they cross, right, those two Y's are equal if you go back to the picture we had in the last one. So all I do is set these two parts, the parts on the right with the X, equal to each other. That's right here. And then solve for X. So there you go. X is 200 hats. And that's what you were being asked for, was 200 hats. Alrighty, so again, as I mentioned, I'm going to expect two equations from you. An income equation and an expense equation. So we're going to start out with the expense equation. Let's read the problem first, I guess. It's probably not a bad idea. A puzzle expert wrote a new Sudoku puzzle book. His initial costs are $864. So whatever that is, that's his cost before he even begins. Maybe that's development or something. Binding and packaging, so it's 80 cents to make each book. The price of the book is $2 each. How many copies must be sold to break even? So again, you write two types of equations. You write an expense equation and an income equation. The expense equation, they both start with Y equals, right? Both start out with Y equals. The expense, I have that initial cost of $864. And then I have 80 cents each book. And again, X, I forgot my let statements, right? Y is income expense, and X is number of books. Again, either made or sold, doesn't matter. Alrighty, so there we go. Back to the matter at hand. I have 864 plus 0.8x because it's 80 cents each book. The income equation, a little simpler. It is Y, that's my income, equals $2 for each book. That's what I make. So, again, break even is when expenses and income are equal. So, this Y here and this Y here have to be equal. In other words, I say that 864 plus 0.8x equals 2x. So when those two things are equal, this one's easy enough to solve here. We subtract our 0.8x, so I get 864 equals 1.2x. Divide off my 1.2, and x is 720, and don't forget to label it as books. That is the break even. So after 720 books, they start making a little bit of money, right? He starts seeing a profit of 120 per book. Again, income expenses, two equations must be written, set them equal, solve. Of the three types we're doing, I think this one's probably the easiest in my opinion. Okay, so I know I get a little bit giddy, you guys think I'm a nerd, but this is one of my favorite types of problems. They're called mixture problems. And it's not my favorite because it's like easy or something. It's my favorite because you get to do a lot of thinking. And you can use this to solve a lot of things. And I mean like real world things. Or especially if you're like me and my sons and you do stupid stuff. And sometimes things blow up or burn down. I think these are kind of fun, and we do actually use these. If again, you will use this if you go into chemistry, in science class, things like that. So it's a really valid thing for you, especially for you folks in the advanced classes. So we're going to read that little green note to the side again this time. It says, I'm going to read the problem first, sorry. A dairy owner produces low-fat milk containing 1% fat and whole milk containing 3.5% fat. Well, I didn't know that. There you go. Now you know what whole milk is. How many gallons of each type should be combined to make 100 gallons of milk that is 2% fat? So the idea is this person is taking 1%, so that, the really low percent milk, and whole milk, and it's going to turn into the 2% milk. So your first step in this is to write a system of equations. So now this is really important here. X is the number of gallons of low-fat milk. Y is the number of gallons of whole milk. So it's your two things that you're mixing together. It's number of and number of. So if I say, ounces or whatever, liters, it's the number of those for each of the two kind of things that you are going to be mixing. What do the percents mean when used as coefficients? So when you're writing these two kinds of equations, you have two kinds again. So last one we had two kinds. We have two kinds for these. You're going to write the total equation, I call it. This one's total gallons, but it could be total of whatever. And you're going to write the mixture problem. So total problem, or total equation, and mixture equation. Notice how they look very similar. You have here the number of gallons of the whole, or low fat, I'm sorry, and number of gallons of whole to the total number of gallons. That's the total equation. Here you have almost similar. Look, X and X, and then the 100 is still here. But here is the percent, 1%, 3.5% expressed as decimals. And here 2% expressed as decimals. All of these look almost exactly like this. If I give you coins and it's a mixture coin, this will be the value of the coins and the total dollars, kind of thing. The first equation, so over here on the side, it says the percent describe the fat concentration in each type of milk. If you multiply them, times the number of gallons, the idea is to go get the total in the end here. So the first equation is easy to solve for either X or Y. So that's why substitution is going to work so nice for these. And it'll be a lot tougher to try to create these, if you're going to do elimination or something like that. But substitution will work just fine. So we're going to take the first equation, we're going to solve it for X. I mean, you could have easily just solved it for Y, no big deal. Either way is fine. And then substitute this, the 100 minus Y, down here for X. And so right there. Little distributive property, fun. And I'll let you take a second to look at the algebra here. And over here, don't forget to multiply on the right side as well. And we find that Y is 40. So if one of them is 40, go back down here, a little substitution again, the other one is 60. So we're going to have 40 gallons of Y, and we said that Y is the whole milk. And we're going to have 60 gallons of X, and X is the low-fat milk. Mix them together, it makes 100 gallons of 2% milk. There we go. So again, to review, two types of problems. You write the total equation, and you write the mixture equation on here. So when you ask for help, I'm saying, did you write the total equation? Did you write the mixture equation? I will ask you those questions. The answer better be yes. Okay, so here's a mixture one, right? Let's go ahead and read through it carefully. One antifreeze solution is 20% alcohol. So, 20% of alcohol, the other must be whatever ingredients, right? Another antifreeze solution is 12% alcohol. How many liters of each solution should be combined to make 15 liters that are 18%? So notice, by the way, in order to do things like this, you have to have one that's above the percent and one that's below the percent. So you can dilute it is the idea. So you're taking that 20% and pouring some 12 in until it reaches 18%. Does that kind of make sense there? Two types of problems we had. We said we have a total equation and then a mixture equation. So we're going to write both of those. We're going to write a total equation and a mixture equation. Total equation. Oh, by the way, we need to write ourselves some let statements. So let X equal liters of 20% and Y equal liters of 12%. Okay? So we say that we have the number of the liters of X, right? That's 20%. Plus the liters of Y, that's the 12%, is going to be 15 total liters. So the total equation is usually the simpler one. Then the mixture equation, that's where you tack on the percents in decimal form to the X and the Y. And then the percent to the total at the end. So we know that the 20% equation, right, that's 0.2 as a decimal, times the X, that's the amount of it, plus 0.12, that's 12% as a decimal, times the amount of that 12% stuff, equals the 18% I'm shooting for, times the 15 liters. If it was going to be 20 liters, you'd have a 20 in there instead. Or if you're shooting for a I don't know, like a 15% mixture or something, or 13% mixture. The 0.18 would be that instead as a decimal. Now, on these, it's obviously easier to solve for one given variable with the total equation. So I'm going to say that y is equal to 15 minus x. So that part right there, that's what I'm going to use to substitute into this equation for y right here. So let's do that. So I have my 0.2x plus my 0.12, and then we're substituting for y over here, the 15 minus x. All of that equals 0.18 times our 15. Okay, give a second to soak that substitution up, make sure we did it right. Then, let's go back and work some algebra fun here, right? So, we've got the 0.12x is going to be carried down, or 0.2x, I'm sorry, plus, and then we're going to distribute that 0.12. That's going to give me 1.8, there we go, it's a little clearer, 1.8 minus 0.12x equals, and then we're going to multiply that right side out, 2.7. So now we're going to go back, combine some like terms over here. That's going to give me, let's see here, 0.8 x on the left side, and we're going to move that 1.8 to the right, right side of the equal sign. So it's going to give me 0.9 over here. Divide off that 0.8 from the x, and x is going to be 11.25, and don't forget to label that as liters. So of the 20%, right, the 20% solution, I'm going to use 11.25 liters. That means I go back and we're going to do a total of 15 liters. So 15, right, 15 minus my 11.25 means that y, so y equals that, y is going to be 3.75 liters. Again, that's the 12% stuff. So you start out, again, mixing together 11.25 liters of the 20% stuff and 3.75 liters of the 12% stuff, and you get 15 liters of 18% when you combine it all together. So again, two types of equations, you're right. The total equation and the mixture equation. Every one of these looks just like this. This also applies to coins, when you have total values in there and things like that. Alrighty, third type of problem. These are fun. And you'll see in your homework, you'll see ones like this where you're paddling up and down a river or walking against or with a, what are those like sidewalks that move in airports, things like that. Which I was promised, by the way, when I was a kid with the Jetsons that we'd have all of our sidewalks be like that. Still not happening. But anyway, so this is when a plane travels, and again, all these kind of look this way. When a plane travels from west to east, right, from west to east across the U.S., notice the way the arrows are going here. The steady west to east winds act like tailwinds. That means it pushes the airplane. This increases the plane's speed relative to the ground. So when a plane travels from east to west, though, the same winds act as a headwind, so it works against them, like swimming upstream. This decreases the plane's speed relative to the ground. So here's the idea. Here's your ground speed, okay, and here's your air speed, and you add it with the wind speed, and it makes you travel faster. When you go the other way, from east to west, so going to the left if you prefer, right? Your airspeed, right, this is the airspeed that's pushing you, or working against you, rather. It actually slows you down, right? I'm sorry, this is the wind speed. I'm sorry, I do apologize. The wind speed pushes against you, rather than with you like over here, and it actually slows you down with respect to the ground. So it's like, notice it pushes against the idea, slowing you down. Okay, got that? Now I kept that up the top so you can kind of refer to that as we're working here. And here's, I think, kind of a cool graphic showing how that works. So it says, a traveler flies from Charlotte, North Carolina to Los Angeles. Notice that's going west, right? So of our graphics up here, that's where the wind's pushing against you. At the same time, another traveler flies from LA to Charlotte. Hopefully they don't, run into each other. And you've got, this time, this is the one up here where the wind is pushing you. The ground speeds are shown below. What is the air speed? So you got to go back and calculate, how fast they are actually going here, right? The air speed versus, the ground and then the wind pushing for or against them. Guess what? Again, two types of equations. Work with all these. Again, this is the up and down the river ones. These are the ones that this you'll see where I think on my quiz or test there's like one of those airport sidewalk things that you just stand on and they move you along, and or you walk faster on them, or like my dorky kids walk against them. Use the ground speed with the tailwind and with the headwind to write the system. A is airspeed. W is wind speed. We were given the ground speed, right? So when you're traveling here, notice with the wind, right, your ground speed was 550. When you're traveling here against the wind, it's actually 495. So there's the constant on the end here. And again, we got to figure out what these different parts is. So airspeed is airspeed, right? The wind speed is something that isn't going to change. It's either going to work with you or work against you is the idea. So A plus W is 550. A minus W is 495. I think these kind are easier. I like them better. So anyway, except for the mixture ones. Love the mixture problems. So here, the great thing is elimination makes it so easy. Because look, you have a negative and a positive W. Boom, wipes out the W's. So we add them together, 2 A's plus 0 is 1045. Divide off our 2, and airspeed is 522.5. That's the easy part, right? Now that I know the airspeed, I can go ahead and substitute here, and doesn't matter which one I use, and I can find the wind speed of 27.5. So again, the wind working with makes you go faster. Wind working against makes you go slower. All these kind of look the same. Okay, so something I may not have mentioned in the last one is we assume the distance was the same in both, because you have Charlotte to LA, LA back to Charlotte. Same distance. We assume you don't take some squirrely gig route that takes you all over the place. Okay, so this one, very similar problem. You are upstream at a speed of 2 miles per hour, right? So that's like your ground speed in the last problem. You travel the same distance downstream at a speed of 5 miles per hour. What would be your rowing speed in still water, right? So, that's how much you're putting into it, right? That airspeed piece. And what would be the speed of the current? So that's like the wind speed in the last problem. Now again, we assume you're going back and forth the exact same distance. That's the important piece of this. If you went farther than one or the other, then that doesn't really work for this, because it is writing two equations that do the same thing. So remember, we have a with the current and an against the current, just like with the wind speed in the last one. So we need a little let statement going on here, though. Let me get this up and out of the way. So we need let statements here. Let C equal current speed, so the speed of the current, the water. Okay, bad handwriting there. R is your row speed. Okay, so again, we have the with the current and against the current. So we have row speed plus the current, so you're rowing with. That was your 5 miles per hour. We have the against, your row speed minus the current working against you. That was only 2 miles per hour. So you can kind of start seeing that. You could probably, a lot of you do these in your head, I'll bet. But anyway, so the nice thing is these really lend themselves well to elimination. So I'm just going to carry this one over here, and we're going to have the R minus C equals 2. So we end up with 2R equals 7. Divide off that 2, and R is 3.5. And the label is miles per hour. So your rowing speed, you row at 3.5 miles per hour in calm waters. I don't know if that's fast or slow, I have no idea. Alrighty, and then we go back and we know that if we use the one of these two, right, doesn't matter which one, and substitute back in, so we can say that our 3.5 plus the C, I'm going to use this equation obviously, equals our 5. Subtract out the 3.5, and C is 1.5, and that's miles per hour. And again, that's the current speed. So the speed of that you row at is 3.5. The speed of the current is 1.5. And you can see up here in these two equations, when you work together, so you row with the water, you go 5 miles per hour. When you row against it, you only go 2. It slows you down. Part B, this is kind of fun. Suppose instead you row at 3 miles per hour, and you have a faster current, 4 miles per hour. What happens when you row upstream? Well, you don't. You don't go upstream. You're going to have to row faster or wait till the current slows down or something like that. Otherwise, you're just going to be rowing and going backwards because it's pushing harder than you row. So there you go. All right. So again, please notice the patterns here. Remember, math is the study of patterns. So look for the patterns. Look for how these are all similar types of problems. Same thing here. I'm going to ask you, if you ask me for help on ones like this, say, did you write your two equation? Did you write your with the current and the against the current, whether it be wind or water or the moving sidewalks? Two types of equations.